What I'm going to do today is show you a little bit about how Cobalt thinks about managing uncertainty on its exploration programs with some examples using joint stochastic inversions on gravity and magnetic data. So when we do inversions at Cobalt, we never do the one optimal, smooth model, pretty inversion. We just don't use that tooling. What we like to do instead is these stochastic inversions that allow us to probabilistically generate many models that all fit the data equally well. One of the approaches that we use is something called parametric inversion. So here we parameterize the subsurface with simple shapes that allow us to describe the features that we're looking for in that subsurface. These might be as simple as like a sphere, in which case you've got a center and some sort of radius. Might be something more complex, like the one I'm going to show you today, using an ellipsoid, where you've got a shape and a size and an orientation. But we can build up these parameters to describe quite complex objects. We can describe a layered Earth. We can describe a fault. It'll have a point on that fault and a strike and a dip and an orientation. And there'll be like a vector that tells you the throw, the offset along that fault. So we can build quite complex models with these. We've even got some new tooling that allows us to generate complex intrusion shapes. But today I'm just going to show you this relatively simple version with ellipsoids. Once we have some way of describing the subsurface, we need a simulator. We can do this with a direct physics simulation. Build a physical property model based on our parameters, and then compute the gravity, magnetic, EM response, whatever it is that we want to look at. Or we can use a machine learned surrogate model, where we train up a machine learning model to predict that physics-based response. Today I'm just going to show you direct physics simulations. So now we've got a simulator, and we've got some sort of parametric model of the subsurface. We need to sample that model. And so we generate a prior hypothesis on what we think each of those parameters is going to be in the subsurface. For example, we might have a histogram that defines what we think the physical properties are, the densities or the magnetic properties, or the size or the shape. That's one of the parameters, and we'll define a hypothesis of what we think that distribution looks like. That's shown with the light blue histogram down here. We'll then draw samples from that distribution to populate our subsurface model. We'll use the simulator to simulate the physical response from that model. We'll compare it to our observations. If it's a good fit, we'll keep it, and we'll keep that sample, and we'll put it in our posterior set of samples. If it doesn't fit, we'll move on and find another one. So that posterior set, those are the subset of our prior hypothesis samples that are also consistent with the geophysical response. And so that is our model of the subsurface. You can see from this histogram that it doesn't look the same as our prior hypothesis. We've gained some information here. If that histogram has a very tight, narrow distribution, it means we've got a really confident prediction about that parameter in the subsurface. If it's wider, then our confidence is less. We can also measure how much it moves. How different is it from our prior hypothesis? If it moves a lot, then we've gained a lot of new information about the subsurface. If it doesn't move much, either we got really good at defining our prior hypothesis, or we haven't learned much about the subsurface. So once we've done this hundreds of thousands of times, we've got a large set of models. This is our posterior ensemble. And we can use statistics to analyze that ensemble of models that all fit the data equally well and make decisions about how we're going to target the features that we're looking for. There are a few ways we can use that. The most obvious way is the panel in the middle there that says, all right, let's just go for the point where we're going to hit the most of the models in our subset. That's the highest probability of success, if you will. But we can also start to ask more interesting questions about, well, how big is this model? Where are the edges of it? And we can specifically target areas where we have lower probability of intersecting the body to answer these questions and gain more information about the subsurface. How deep is it? How steep is it? Those sorts of questions. So this is just another example showing exactly that same framework, but in a little bit more concrete detail. Here, again, I'm just using one ellipsoid to describe the subsurface. It's got size and shape and orientation and some sort of physical property, in this case density, and it's hollowed by density. And this set of models that I'm showing in the animation here are all consistent with the input data. So here, those models fit the gravity data, they fit the magnetic data, and they fit the physical property measurements that we've measured down that drill hole. This is just a simple synthetic example. And then we can compare prior hypothesis. Here, the blue histogram really says, we don't really know what's going on with this physical property. We'll just, anything's possible. We can run the inversion and we can get a prediction about what we think that physical property might be. You can see this histogram is relatively wide. There's a bit of uncertainty here. But if we're looking at just one single inversion result, we don't get any estimate of that uncertainty. But here I can make decisions based on that. So today I'm going to show you a case study looking at nickel exploration. We are seeking mafic to ultramafic intrusions that may host nickel sulfide mineralization. We're not trying to target the mineralization directly here. We just want to identify prospective intrusions where we can then come in and do additional work. We're expecting these intrusions to be dense and magnetic, and we've got some ground gravity data and some airborne magnetics over a particular target. You can see very simply from these data sets that we have two anomalies here, it looks like. They look like they're co-located. We have a really strong gravity anomaly visible on the east side. It's got a magnetic response, but maybe not as strong as the other body, which has a really strong magnetic response, but maybe less of a gravity response. So we can see there's a target, and sure, you could come in and just plonk a drill hole right in the middle of those things and probably have some pretty high confidence about hitting a target. But we want to be a little bit smarter and know what our probabilities are and how much should we invest in targeting what's going on. So we start by generating some hypotheses about what we think we're looking at. Here are two of them. We usually generate quite a few. The possibilities here, we're looking at, perhaps we're looking at differentiated mafic ultramafic intrusions where we might have more of a gabbroic rock at shallower levels, and that fractionates down into an ultramafic rock at depth. Each of those will have slightly different density and magnetic responses. Perhaps we have just one ultramafic body and it's variably altered, perhaps with serpentinization making parts of it more magnetic. But you can see that broadly these hypotheses could be described with an ellipsoid. They've kind of got some width to them, there's some plunge, some orientation, they're longer in one direction than in another direction. So the simple example that I'm going to show you here today uses ellipsoids to try to describe this subsurface, but we could come up with more complex geometries. So now I'm going to show you the inversion result, and it's quite a bit different from most inversion results that you see. So what I'm showing here on the left, the blue line is the measured gravity data and the measured magnetic data on some survey line in this data set over the top of one of these anomalies. The black lines represent 1,000 samples from our posterior model. Those are the predicted gravity and magnetic responses of models that are shown in the animation on the right there. You can see that most of these describe a large anomaly in that location pretty well. Some of them fit the gravity data better, some of them fit the magnetic data better, so there's a bit of a spread, but we also know that this is a relatively simple model trying to describe a complex Earth. So we're allowing a little bit of misfit there. On the right is the inversion result. We're sampling through a whole bunch of those realizations that fit the gravity and magnetic data. We're not just looking at one model, we're looking at many. And this is a subset of about 100 out of 100,000 results that we generate. You can see that even though we're fitting both gravity and magnetics in a joint inversion here, there's a lot of variability in what we're seeing in these anomalies. They're colored up by their density, You can see that there are some that are smaller with higher density, some that are larger with lower density. Some of them plunge to the west, some of them plunge to the east, some are really long, some are really compact. All of that is acceptable. That all fits the gravity and magnetic data. And so we can quantify the uncertainty of hitting a particular target from these results. One way we can do that is we can sample through that set of posterior models. Here, every dot, you can think about it as a virtual vertical drill hole going straight down through the set of models. And we're counting up the number of models we hit on each one of those drill holes. What is the percentage of models that we hit at any one of those locations? And what depth is our highest probability of being in one of those target bodies? And you can see that in the corners, there's almost no probability of finding a really dense body above this threshold that we're targeting. But as we move in towards the gravity anomaly, we get higher and higher probabilities of being in that body. You can see the maximum is something around 80% probability of being in that body at a depth of around 550 meters. But now we can quantify the difference from that model on that body on the left. You can see there's a much lower probability of being in such a magnetic body there. And the depth is now roughly 350 meters for that one. So we can make better decisions on how to target these features. We can do exactly the same for the magnetics. What is the probability of finding a magnetic body above some particular threshold? And you can see, as we predicted, the highest probability of hitting the magnetic body is right at the same location as the highest probability of hitting a dense body. You can see the probabilities here are even higher. We're up to almost 100% probability of hitting a magnetic feature of interest at that target depth. So we drilled these two drill holes shown here. For this first part, I'm only going to show you the predictions and the results for the hole on the right, but we'll revisit the hole on the west side in a bit. So here are 3 panels showing the predicted responses down that drill hole trace. Effectively, what we thought we were going to see before we drilled the hole along the trace of that hole. The first panel is the probability of being in a target feature at any given depth. You can see it starts to kick up around 300 meters depth, and it reaches a maximum somewhere around 550 meters depth, as we saw. The next 2 panels show the predicted range of properties down that drill hole, looking at all of the models we collected. The dark orange band contains 50% of the predictions. The light orange band contains 80%. And the black line represents the median. If you take the median density value across all of the models, that's where you'd be. So you can see also these start to kick up from background levels at around 300 meters, and they peak somewhere around 550 meters depth. But you can see there's a range. Even if we just look at the 50% of the models and give us the tightest prediction, we've still got a range of predicted densities from 3 to 4 grams per cc. Then we drilled the hole. The hole went into a sequence of unusually dense monzodiorites, and within that was a 200-meter sequence of gabbro. There was some pyrrhotite in that gabbro, but no evidence of nickel mineralization, unfortunately. We measured density and magnetic properties on every drill hole we drill, and I've plotted those, density in red and magnetic properties in pink. And you can see that these also start to kick up at around that 300-meter level at the top of the gabbro. They're kind of at their highest through that section of the gabbro, and then they taper away. You can see that our predictions were within the envelopes that we predict. Our measured values are within the envelopes that we predicted, but they tend to be on the lower side mostly. But we can see there's no nickel mineralization in this drill hole, and the hole to the west had similar results. But does this eliminate the possibility of there being other targets on this project? Were these perhaps a near miss of something that might be more interesting? How do we know to walk away? So we take those measured densities and susceptibilities and put them back in another inversion. And so now this is the same style of inversion. We're fitting the gravity data, the magnetic data, but also the density and susceptibility measurements down both of those drill holes. You can see the predicted responses on the left. Some fit the gravity better, some fit the mag better. But the model on the right shows that we've changed the results that we're predicting here. This looks remarkably different from the inversion result that we had before we drilled the holes. What's different? You can see that we've eliminated all of those really high density possible targets. We don't have any of the reds and yellows anymore. They're all in the blues. But even though we've put in all that extra subsurface information, there is still a lot of variability here. Some of them still dip west, some of them still dip east. Some of them are really long, some of them aren't. That is the uncertainty of geophysical data. And if you're just looking at one model, you can't quantify that uncertainty. So we can look at the same predictions about what we might have seen, what we might see elsewhere on the project. On the left, you can see we've almost eliminated any chance of finding that dense body. Maximum probability now, once we've included all that information, is only 10%. So we're not going to find another large mafic or ultramafic body here, it looks like. On the right-hand side, you can still see that there is still up to 40% probability of finding something more magnetic here. So we need to make a decision. Is that important to us? Do we want to chase a 40% probability? What do we think that is, and what could we potentially learn? So just showing you the same downhole plot for that eastern drill hole that we had before, but now because we've included those physical property measurements in the red and the pink, we've got much tighter predictions about what we think is going on in that drill hole. That's fine. I didn't show you the results for the hole on the west side before, but here are what they are with those included physical property constraints. And you can see something interesting in this hole. You can see there's this zone in here with really high densities and very high magnetic properties over an interval about 20 meters at the top of that second gabbro unit. When you look at the core, you can see there's actually a 20 centimeter zone where we've got these clear, strongly developed magnetite bands. So those magnetite bands have really, really strong magnetic properties associated with them. They're clearly not associated with nickel mineralization. They're not a target of interest, but they can easily explain why we were seeing some predictions of, well, there's more magnetic material around here. So we don't need to chase that 40% probability of finding more of this stuff. We've already got it here. We know what it is. We can walk away safely. On this project, we also had downhole EM that told us there were no off-hole conductors. We have PXRF data that told us that these mafic rocks did not have the right chemical affinity for the type of thing that we were looking at. So altogether, we know that there's no additional prospectivity on this project. We can walk away cleanly and happily and move our expertise onto the next problem. Just to give you a different representation of how we can look at these sorts of inversion models, because it's a bit more complex than looking at one slice through one model. Here's a oblique vertical slice through those two drill holes, showing the probabilities that we were talking about before, those dot plots, except on a slice view. Before we drilled the holes in the top panel here, on the left, probability of finding something really dense. On the right, probability of finding something really magnetic. These aren't slices of a physical property model. These are slices of a probability model. You can see they really build up towards that 550 meters depth on the east side. We've got the gabbro right at the top of where we were predicting the higher probabilities to start. And then we can look at how that changed after we included the physical property information. You can see we've wiped out almost all of the potential here, except for that lingering potential of finding some more magnetic material. We know that's the magnetite band. There's nothing more for us here in this project. But if there's one thing I want you to take away from this presentation, It's not that you need to run out and do fancy stochastic conversions on every project. They're really effective at helping you make clever business decisions when under uncertain circumstances, but I want to tell you to always include any subsurface information you can in any inversion you do, whether it's a nice smooth one or a complex Bayesian formulation. You just have to include that subsurface information because there is so much uncertainty in these models, even when you include everything you know. These are 4 ways that Cobalt includes subsurface information in its inversions. This framework, this stochastic framework, allows us to do these 2 on the left that are a bit more tricky to include in normal inversions. The top one, if you've got observations that say there is no target here, that's great information. You should include it in the model. If you know it doesn't outcrop, that's important constraint information. If you've got a duster drill hole over in the corner that tells you there's no target there, that's important information. You can set up your models so that none of the targets you recover intersect those features. We can also use analogs. If you don't have any physical property information, you can look up the Canadian Rock Properties Database or the Australian Rock Properties Database and come up with a distribution of what your prior hypothesis on what the physical properties might be is, and include that in your sampling strategy. On the right are a bit more routine approaches. Of course, Cobalt measures physical properties on every hole that it drills, either in core or downhole. If you know something about the mineralogy and the geochemistry, you can make predictions about what the physical properties are. We know what the physical properties of the mineral, of each of the minerals is. We know we can estimate their abundances based on the geologic information we have available and the assays. We can predict their physical properties, and we can include that directly. That's all I have for you today.
We have time for maybe 1 or 2 questions. Please go to the microphone.
Thank you for the nice presentation and showing the ambiguity of potential fields, not geophysical data. Some geophysical methods, they do not have the ambiguity that we have on gravity magnetic.
I would argue that every geophysical data does.
If you do invert, yes. If you do imaging, you won't. But nonetheless, if we look at the magnetic and gravity data, you have a number of features cross-cutting the anomalies, and you drill right through one of those features that you don't even have it in the model. So now the question is, would you be able to simultaneously add different features in the inversion to add
Absolutely.
more? So you could have plane running while you have elliptical.
Absolutely.
Yeah.
There's no restriction here that says we can only have ellipsoids because I chose ellipsoids. We can combine multiple different features. So I could have a fault running through here that I have a hypothesis on what the offset is along that fault, and I can solve for that simultaneously.
And why was it drilled in that specific position? Because it looked very dangerous. You had the features cutting through the inversion. You did not have drilled that position.
The intrusion was, you can see from the data, but also from the model results, the intrusions were kind of oblivious to that. We know we've got some dikes cutting through the area. They are minor, relatively thin features, but this intrusion didn't seem to be terminated by that dike.
Thank you.
Thank you for the presentation. Have you worked thinking about including remnants?
Oh, definitely. So I didn't point it out. It was on the slide. For that second inversion, because we have susceptibility measurements down the drill hole, we can actually solve for not just the susceptibility, but also the magnitude and direction of remnants. And we did that. And we then sent samples for paleomagnetic measurements to get oriented measurements of that remnants, and they aligned really, really well. Not one-to-one, but they were very well aligned. So we can make good predictions about the remnants if we've got the subsurface constraints from the susceptibility measurements.
Thank you.
Yeah, Nick, that was awesome. So I saw that you do a drill based on sort of the maximum probability that you'll hit the target. use that information to then, further a stronger prior, and you run it again. And I'm kind of wondering, do you ever play around with conditional probabilities? So instead of running that thing again, take that drill hole and say, given I had this happen, what would happen, or what would be the next place I would drill? Do you play around with that at all?
Absolutely. Theoretically, yes, you should be able to get exactly the same result without rerunning the inversion. It'd be a much faster approach, and during real-time analysis of your project, you can do that. So take that initial subset of samples and then compare them against the drill holes is what Devin's suggesting. And just pick out the ones that fit everything. Absolutely. So that's a really efficient way of doing real-time updates while you're doing the drill program. As the previous questioner asked about remnants, I did a bit of a bait and switch here because I could now change the parameterization of my model to include the susceptibility measurements and try to estimate the remnants at the same time. In the original inversion, I was just looking at the total magnetization. And so I actually changed the model, and therefore I'm getting a very different prediction in that second one. But in real-time drilling programs, absolutely.
Cool. Thanks, Nick.